Okay, today we'll start the session on round robin orbiter. Okay, so this is a simple we can call it as like minor project or a simple example using the UVM. Okay, so we already completed all topics of UVM, right? So you understood all topics. So you need to practice. If you forgot, just practice and revise all the topics. Okay, so you will get idea on those. Okay, and so with by using all those topic we'll create a test cases today, so test plan or verification. So yeah, we'll start with the round robin orbiter in UVM. In system verilog we have seen already AHB and router projects, right? So in UVM we'll see this example. So what is mean by orbiter? What is mean by orbiter? We already seen arbitration concept in I2C. I think for your batch I didn't explain I2C protocol. But you know what is mean by arbitration, right? So what is mean by arbiter?
So arbitration is a concept that assigning when multiple masters are in the queue. So to assigning the bus or to slave. So this is the fashion that arbiter
Okay,
is a component that will assign.
okay. So which what are the different types of orbiters we have? What are the different type of orbiters? Okay. So we will commonly face some problems, right? Suppose when there is a shared resources, okay, by multiple agents in the design, so we need to access a shared resource by multiple agents from multiple sources, okay, or multiple masters we can call. So for that purpose if there are multiple number of masters and a single slave, we don't know which master need to access that bus and which master need to initiate the transaction. Okay, so for that purpose in I2C, if you see, there will be multiple number of masters. Okay, so in that to initiate the bus transaction, we have used the arbitration concepts by using end gate. Okay, so same like that, in wherever we use multiple masters or like we can call as a multiple processors to access a common resource called memory. Okay, so any one processor or any one master can initiate the transfer at a time. All multiple masters cannot access that common source, common resource, whatever it is, right? So for that purpose, arbitration concept is required. So in orbiters there are different type of orbiters like priority based orbiter or round robin orbiter or weighted round robin orbiter, like that. Okay, so priority based means whatever high priority master is there which one need to transmit quickly, okay, that master will get the high priority. But round robin orbiter is somewhat different. Okay, so orbiter is nothing but orbiter design is used to ensure that only one source has the access to the common resource, whether there are multiple processors or multiple cores, whatever, it can have only one processor access to the memory designs. Okay, where multiple processor need to access memory using the shared bus. Okay, here by using the shared bus, all these processors will use the uh, uh, will access the resource. Okay, so as I told, there are different type of arbitration techniques used in the design of orbiter based on the different requirements. Okay, every design will not have the same requirement, right? the design have its own requirements according to the specification. So based on the specification, we will use different types of orbiters. Okay, so in that, round robin orbiter is one of the commonly used arbitration mechanism in the designs. Okay, so what is mean by round robin arbitration? Do you have any idea in this? Okay, so round robin orbiter is nothing but it is a one arbitration policy, okay, which is in a token fashion. Okay, how the tokens will be given? First comes first, right? So the token passing scheme, wherever we see, so the same policy will be applied to the round robin arbiter. Okay, so among the multiple requesting agents, without any starvation, will access the resources. That is the round robin fashion. So there will be number of cycles based upon number of masters, or based on number of processors. Okay, so in each cycle, one of the master will have the highest priority to get the shared resource. Okay, then that will be rotated in a round robin order. Suppose if there are 5 masters, the master 1 will get the priority first, then master 2, master 3, master 4, master 5, again master 0. That is nothing but round robin fashion. Okay, so if any master does not need any access to that resource in that particular cycle, then the next master can get the priority, so that the next master will get the bus. Okay, so that it can able to do the transactions. Okay, simply this is the round robin arbitration. Have you understood, everyone? Hello.
Well, this priority will be always sequential or whichever comes first. Like the 1, 2, 3, 4, 5 continuously it will go, or
Yes,
randomly it will
continuously, not
take some.
randomly. It is a continuously in a sequential manner, and after last master completed, again it should come to first master only, not in between any of like third master or fourth master. It is not like that. After completion of last master, it should come to first master only.
Okay. Okay.
Okay, that is nothing but round robin
So,
arbitration.
ma'am,
So we'll, yes, tell.
so it will go one by one, and let's
Mm.
say if master two is not ready to use the bus, so
Mm.
then first it will go, after completing master one, it will go to master
Go
two,
to
as
master
it is
3.
not, yeah,
Mm. Yes,
as it is not willing to use the bus, then it will go
mm.
to master three, like that.
Master 3. Yes.
But what is the advantage we'll get, ma'am? Here, the lot of delays we will get, right? If master
Uh,
4 has some
See,
highest
round
priority.
robin arbiter, yes, round robin arbiter have the disadvantages also, because we cannot give a specific master which is a very high priority. Once the master priority is given, it will be rotate in a round fashion. Okay, in middle, if any if any high priority, we cannot initiate the transfer
Yeah.
at that particular time. So that is the disadvantage with the round robin arbiter. So that's why we are moving to the priority arbiter, and some of advanced arbiters also there.
Okay.
Okay, like this is a basic arbiter. Just for example, we are just discussing it's a basic arbiter. Okay,
Okay.
everyone clear? Okay, so this is what round robin block diagram. So if there are 4 number of processor in every SOCs, there will be n number of processor, right? Not single processor. N number of core is nothing but n number of processor. So every processor need to access some memory. Okay, same shared resource is nothing but the memory. So which processor will access that memory at what time? Okay, so there are 4 number of processor. By using the round robin arbitration, first processor 1 can able to access the memory, then processor 2, then processor 3, then processor 4. The final state mission will be in a round fashion. Okay, so this is a simple block diagram for this. So first, what happens? Arbiter will be based on the priority of the requesters. It will be set that every requester get resource equally. Okay, so every resource will get equally. So the priority of every requester keep changing with each allocation of the resources. Okay, so what is the working principle of the round robin arbiter? We'll see what is the working principle. So initially, when there is no request, okay, when there is no request, the first requester is given to highest priority. That means the first processor will get highest priority. Now the request from next requester is given to the lowest priority than previous one. That means processor 2 will get the lowest priority than processor 1. Okay, and suppose if requester with highest priority is allocated the resource, okay, and now we can change its a priority to the lowest because it already completed its a transaction. Once the transaction has completed, okay, again automatically it will be set to the low low priority. Okay, so and then another requesters get incremented one by one. Okay, like incrementing fashion. Processor 1 plus 1, nothing but processor 2. Again, once the processor 2 done its task, then again it's set to the lowest priority. Like that, it will be continued. Okay, so how you will write the logic? How you will control the different requesters here? Processor is nothing but request. The input will be the request, output will be the grant. Okay, once any master requested, then we need to give the grant. Arbiter will grant. That means it can access the bus. Particular master can access the bus, right? So how you will write the logic for that simple logic?
Yes, ma'am. State machine, we will take it and for 4 states will be. One is
Mm.
ideal state. Whenever request comes from the processor 1, it will go to the next state.
Okay.
It will use that process till that complete that functionality. It will be in the state 1 only. Once that functionality is completed, then it will go to the state 2. And there it will
Okay.
wait. When it comes in the second one, then it will go to it will wait for the till functionality completed. After completion of second state only, it will go to the third state. If there is a no request from the third, it will go to the fourth. If it is a no request from the fourth, then it will come back to the first one.
Okay. So this is very
This is
simple finite state mission compared to remaining protocols, whatever we did. It is a very simple finite state mission. We can write very simply. So next one is a block diagram. So what? Not block diagram, pin diagram. So what are the different pins? What are the input pins and what are the output pins? So input is reset and acknowledgement, clock, and request. Request 4 means 4 masters, 4 requests. Okay, and output is a grant. Okay, for each request, whenever request has high, so grant will be given, right? So grant is also 4-bit. Request is equal to grant. That means size in terms of size. This is the pin diagram for round robin arbiter. Based on this only, we are going to write the design program. Okay. So what is the difference between round robin arbiter and the priority arbiter, normal fixed priority arbiter? What is the difference between priority arbiter and round robin arbiter?
Round robin will always works in the sequential direction.
Mm.
So always sequential it will go. Whenever priority bias means when it is in the first state, after that immediately if a priority comes to the fourth state, means it will jump to the fourth state and it will
Okay.
execute the fourth one.
Okay.
But
So
how priority is decided, I have a question on that.
sorry.
How priority is decided? That I have a question. Like
How priority decided means in terms of design will allocate the priority based
okay.
on which master need to access some transactions. Based on your transactions, which master need to get highest priority, you can allocate that value to the design. We can access
Yeah,
that.
yes. I got it. Yeah.
Okay, so here what is happening in priority arbiter? If you see first request 0, then request 1, next 2, next 3. Again, it is not getting to the request 0. So in this case, if you are assuming the priority of request 0 is high, then priority is decreasing in order request 1, request 2, request 3, like that it is decreasing. So when requester with the highest priority is requesting for the resource, we will neglect lowest priority requesters. Okay. So that is suppose if you want to, if it has the highest priority at request 2, then next priority will be request 3. That will be in that fashion, but not as a round robin. So what are the advantages means this is a basic priority arbiter which is used to allocate the resources based on its priority, and in priority arbiter the priority of requesters are fixed, not like a round robin arbiter. Okay, so one of the main advantage is over the round robin arbiter, we can give the preference at any particular requester. As I told you, if request 2 has high priority, if any interrupt is getting, so request 2 will get highest priority. So that is the advantage compared to the round robin. Okay. So what will be the working principle of priority arbiter? What is the working principle of priority arbiter?
This FSM, we should have access to move to all the states. From each state, there will be to all the states. Whenever it is required a highest priority, it will move to that state. That is how we have to code the logic.
Okay. First of all, if there are 4 number of masters or 10 number of requesters, we need to check all requesters. We need to examine all the requesters first. Then if any requester need highest priority, then we'll give the resource to the highest priority. Okay, then we will move to the next highest priority requester, whichever request in the among these requests. So we'll choose like that. Okay, so what happens? Priority of the requesters are remains unchanged in this way. Okay, so the requester with highest priority again make a request. Suppose it will be served before serving the previous request of low priority. So it can again make a request if it is needed. That is a main thing in the priority encoder. So that process will be continued if there are no more requests are left. So that process will be continued. But whereas round robin arbiter, even if some masters are highly demand in the middle, it doesn't allow that. Okay, it will be in a round fashion only. So that is the disadvantage. If we need to give some importance to a specific master, we cannot do that. Even if we want to allocate resource to a particular unit, between two, like particular unit frequently, okay, like if there are two successively, if we allocate round robin arbiter, we cannot do that thing. Okay, two successive requests and two successive requests like that also we cannot give the access. That is the disadvantage. Okay, everyone understood? The main intention is now not about the design and all. The main intention is UVM program. Okay, so here we need to concentrate mostly on UVM. So that's why a simple design I have taken. Okay, everyone clear? Okay, next thing. So these are the advantages and the disadvantages. I think everyone clear, so that we can move to the design. If you have any doubts, please let me know so that we can discuss clearly. Okay, so coming to the design. So module, arbiter, clock, reset, request, grant, and COM request is nothing but communication request. Communication is nothing but for bus access. Okay, and ports declaration, you already know, request is of 4-bit for request size, and grant is also 4-bit, and communication request is, if it is high, then bus is free, so that we can initiate the transaction. If communication request is low, bus is not free. Okay, and these are encoded grant and encoded latch grant and latch communication request, mask enable, latch mask or latch mask. So if there are 4 masters, suppose here requests are 4, right? Then masters will be, L mask will be 2 states. 2 states means each request will be 4 request means 4 combinations, right? 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 for request 0, 0, 1 for request 1, 1, 0, like that. That is a L mask. Okay. Next, mask enable. So how we can make mask enable? Either request 3 or request 2, request 1, request 0. Anyone will be high and not of L communication request. L communication request means 0. Okay, so here high means the bus will be free. Okay, so that's why we have taken this statement. And always at the rate of negate, reset, initialized with 0, grant and mask, both variables initialized with 0. Always if mask enable is high, mask 1 is getting encoded latch grant of 1, and encoded latch grant 0 is assigned to mask 1 and mask 0, else the same value. Next, here is the main logic you need to understand. Always at the rate of posage clock, L grant of 0 is equal to, so what is the L grant of 0 means? Request of 0 should be high, right? Request of 0 should be high, remaining all must be 0, so that it will get the access. So how here L request, so it should be 1, and L mask is 0, 0, then request 0 will be high, and L mask 1, 0, 0, 1, 0, 0, so that the design, if you observe here, okay, if L mask not L communication request and L mask of 1, which is negotiated, and L mask of 0 and negotiated with request 3 and request 2 and request 0, because request 1 for 0-1 combination, request 1 will not be there, and for 1-0 request 2 and 1-1 request 3. Okay, so there will be 0, because request 0 should get the bus, right? So that is why, based on the L mask, we are selecting the request. Okay, same as L grant 1. So request 1 is getting here. Request 1 is a high. Remaining all are eliminating each request in 1 0 1 1, like that. So next, for grant 2, also same. Request 2 is getting high, and grant 3, request 3 is getting high. Okay, so just if you have confusion, I will share you the design after the session. Check very clearly what is happening in the design. Okay, so that you will understand very clearly. And communication request. Yes, tell.
Ma'am, what is that L mask, ma'am? I couldn't understand the functionality of that L mask.
L mask is nothing but the signal which we are giving, mask signal. Okay, for request, to enable the request. Okay, for that we are using the mask. Okay, for request means we are taking 2-bit mask. Based on the mask, we are enabling the request.
Okay, so if L mask is not high, it means request can't be raised. Is that
Not
so?
high, not high. See, L mask is a 2-bit, right? 2-bit means 4 combinations. 0 0 means for request 0. 0 1 means request 1. 0 2 1 0 means request 2. 1 1 means request 3. So based on that, we are selecting here. Okay, masking
ma'am.
the.
So if for example L mask is 0 0, and if you are using negation of L mask, then it becomes 1 1, right?
That will be become 1 1. 1 into 1. So request 0 is selecting here.
Okay.
If all are 0, output will be 0, right? So request 0 is selecting here. Based on the L mask and communication request.
Okay, ma'am. Okay, I'll work on this logic. Yeah, it is little confusing. I'll try to work on the logic now.
Okay, sure. Okay. So next, L communication request is equal to request 3 and L grant of 3. Okay, or request to L grant of 2. That means communication request is nothing but which won the bus. Any one of the request only can won the bus, nothing but bus status. Request 1 high means L grant also high. So any one of the requests will be high at a time. Next, encoded logic, encoded L grant. So for the grant signals here, and assign encoded grant equal to encoded latch grant, because here we all taken as a temporary registers, right? So that's why assigning to the outputs. Communication request equal to L communication request, grant equal to L grant. So this is the simple design for round robin. Yes.
Ma'am, why there is a need of taking L bridge? I mean, L type of this one. Why can't we directly assign like communication request? Why can't we
See,
directly
here we
assign
are
those values to
using L mask, L grant signals in the procedural blocks. By using the procedural, we cannot assign, right, these things. So that's why we are taking some temporary register. With help of that, we are doing the functionality, and then we are taking into original variables.
Can you explain that? I mean, what is the consequence that we have to face if we don't use the temporary registers or what?
If we don't use the temporary register, so how can we write the like we can write the program, but I felt even this is the easy, like I have taken the temporary variable in this fashion, so so no obligations between both variables, right, in terms of functionality, so that's why. So
Because
just
if we are using extra internal registers, it will cause more storage. So what is the extra need? I mean, definite need that we have to use temporary internal registers.
Here here we have used to overcome that issue only see here L grant is nothing but if you use directly grant, what happens? So L grant is nothing but here encoding is happening, and based on the latch grant only the encoding logic is available, right? So like that, by using L grant, we are assigning directly to the grant so that we can avoid some internal race conditions here.
Yeah, output we are not supposed to use it as a input. The declaration, whatever we have at the output, that we are not supposed to use it as a input. So that's why we are using the internal signal. If I am
Yeah,
not wrong.
yeah, first
Because
I
here
told
output
the same. Because as we are using procedural and continuous both here, so temporary, if you take temporary variable, that will be good. Okay. You can try without taking like that. You just try with a different finite state mission without this logic.
Okay.
Okay. So any other doubts in the design? You need to work with the design so that it will be not confusion. Next, coming to the UVM. So I think everyone remember the concepts of UVM, right? So I think everyone remembered the concept, right? So just you can explain. So what is the difference between sequence, sequencer, and sequence item? What is the difference between sequence, sequencer, and sequence item?
In sequence item, we have to define our variables that are which are our inputs, and in sequence we will make them as a randomization in the body. And sequencer is just like a router between sequence and driver.
Okay. Any other answers? Others?
Sequence items are nothing but they store the transactions, we can say that, and sequence is used to generate the sequence item, and sequencer is used to establish the connection between sequencer and the driver.
Okay. So sequence is nothing but it will generate the sequence items. Nothing but in the system Verilog there is a generate block, right? Generate block is nothing but it will randomize the n number of scenario and it will send to the driver. Same here, sequence generates the number of sequence items and it's sent to the driver through sequencer. Okay, so sequence is written by extending the UVM sequence, because all UVM in UVM all will be derived from its base classes, right? From its libraries. So UVM is derived from the UVM sequence and UVM sequence item. So, and UVM sequence is also a parameterized class, right? That means it will define the send or receive to the driver. Okay, mainly what it will have the request and the response handles. Okay, so what is meant by request? Request is nothing but it will provide the information to initiate the process of that particular functionality, right? And the response is nothing but it will provide the information about the completion or the status of the that operation. That is nothing but request or response, which is a parameterized class. Okay, so here if you see the base class, sequence extending from the UVM sequence and sequence item. So sequence item for that created as a request and object util. So what is meant by object util? Tick UVM object util.
It is used to register the base sequence.
So it is used to register the object. Object base sequence is nothing but the object here, right? We know the factory registration concept. Okay, by avoiding the ID, type ID, and wrap, we just use the macro tick UVM object util. So if you want to create the component, then you need to use the component utils. So first we need to create the item or the request. That is main thing. And we need to wait for the grant, right? And then function new. So what is function new? Create. Already we've seen in the system verilog, right? Next, task body. In the task body, UVM info. So in system verilog, we have used $display, $monitor, $scoreboard. Sorry. Another one I didn't remember. Okay, $display, $monitor, like that, right? $write. So there are disadvantages with that. So if there are more number of dollar displays in the total TB, it will be very difficult to avoid if unused $display are there. Automatically, it cannot generate for each statement, right? So info, UVM info or UVM warning, UVM error mean these are automatically they will be generated. Okay, so UVM info is the macro, get type name, so base sequence inside body, UVM low. Okay, so what is UVM low? What is mean by UVM low?
It's a verbosity level.
So UVM low, UVM high is the verbosity levels. Okay, UVM verbosity level. So if you don't remember, just go through those. Okay, we already discussed. And tick UVM do request. So where we use UVM do, I already told you one time. UVM do.
Ma'am, it takes sequence item as an argument or a variable.
Okay. So UVM do is nothing but it will create the item and it will randomize the item. Okay. So whatever create plus randomize directly we can use the do. Okay, those will be without like it will skip those tasks. Okay. And that is about the sequence. Next, sequencer. So what is sequencer? Sequencer also same component, created the class sequencer. So it's a component, UVM utils, and function void build phase. So what are the UVM phases? What are the different UVM phases? Build phase,
Build
connect
phase,
phase.
and extract phase, final phase,
Okay,
start.
build phase. Okay, we need to come in order, right? Because those will be executed in a order, right? The build
Order
phase,
phase.
connect phase, end of elaboration means what is the end of elaboration? Start of simulation, run phase, phase,
and extract phase, final phase.
report phase, final phase. Okay, okay. So build phase is nothing but it will build entire TB infrastructure.
Component, test bench,
Yes.
component.
From higher level component to the lower level components will be created. Okay, in the connect phase, we'll connect all the components. So here we just taken the build phase. Okay, and then sequence items. Sequence item will be extended from UVM sequence item static int some ID. We have taken some maximum ID just to generate some value here. Okay, so int ID request and communication request is a output and grant is also output, right? So function new super dot new and ID equal to max ID plus plus. Okay, just for um uh, for synchronization between number of transactions. Okay, next UVM object utils begin. Why we use begin and end? If there are multiple number of statements, we use begin and UVM field int request comma UVM all on. Okay, so what is meant by UVM all on? All operations will be turned on. Like copy, compare, print, reference, all these will be on. Okay, so that is what. Next, driver. So what is UVM driver?
It will drive the transactions and it will pass through to the monitor.
Okay, so same as a system verilog only, but here we use mostly phases. Okay, but in system verilog, there will be no phases, right? Here there will be, in terms of phases, we'll connect all the things. Here we have the get next item and put next item, try next item, like that. But whereas in system verilog, we have used mailbox put get method, but here we use the TLM port for sequence item, TLM port for get and put. Okay, so what is a get next item? What is the difference between get next item and try next item? Okay, if you don't remember, just revise the concepts. Okay, see, class driver extends UVM driver and passing the argument sequence item, virtual interface, you already know, and component creating constructor, function void build phase of UVM phase. Super dot build phase calling the super build phase, and if UVM config DB. So what is meant by config DB? What is meant by config DB? We already discussed, right? Config DB is nothing but it will
is
have
the
all
subset
the
of resource.
information.
Is the subset of means resource DB, and it provides us like central access to store and receive the data.
Okay, so whatever the requirement according to the verification plan, according to the specification, we can all are user defined, right? So if you want to select the agent, different type of agent, or if you want to select the scoreboard, enable or disable, okay, all the things will note in the config DB. Okay, so we can store in the config DB, nothing but the database. Okay, like for RAL model, yesterday we have discussed registered database, right? Like that config database. So config database virtual, that virtual interface name, get this, you know this how to create, right? So then UVM fatal error, if that condition is fail, then task run phase. In the run phase, sequence item port dot get next item of request. So this is regarding TLM port. Okay, so UVM info get type name format dollar format and writing the printing statements. Okay, next VIF.id equal to request.id. Whatever we are generating from the sequencer, that value will be sent to the DUT via virtual interface, right? So same thing as a system, same as a system log. Next, sequence item port dot item done. Once all transactions completed, item done. That is one method in the driver, right? Next one, monitor. Monitor also opposite to the driver, same as a driver. So class monitor extending from the UVM monitor and virtual interface, creating the virtual interface, and analysis port. So why analysis port? What is the difference between TLM port and the analysis port?
Analysis port we need when we connect multiple one to many.
Okay, one to many. There we use the analysis port, right? So here UVM analysis port, sequence item, item collect port, and sequence item created monitor item is the instance, and component util for monitor, then constructor, then build phase. In the run phase, we are from the DUT sending to the monitor, the data is sending to the monitor, mon item dot id, mon item dot request. So according to that, if wait, see, you need to check the conditions. You already know system log, right? That's why I'm not telling about in detail about the conditions and all. You know how the monitor block work and driver block. So next, UVM info, the printing statements. Again, for next negative edge of the clock, the grant data and the communication request, both are outputs, right? That are sending to the grant and communication request of monitor signal. Next, UVM info statement and item collect port, the write of monitor item. So write method. So this is all about monitor. Next thing is interface. Interface, we already know. All the data must be declared with the logic, inputs and outputs. There we use the clocking blocks and the mode port. So here we use one clocking block for both driver and the monitor, and communication request taking with #1 delay, simple clocking block. Okay, and scoreboard So in scoreboard is main important because we'll write the reference logic here, right? So UVM class scoreboard extending from the UVM scoreboard, UVM analysis board. Next sequence item, we have created the memory. Here we have created the queue. Next, creating the component. Next, build phase, write transaction, and run phase. So what happening in the run phase? Prevent grant is equal to initialized with a 0. Expected grant initialized with a 0. Forever wait item q dot size is greater than 0. If item q dot size is greater than 0, then SB item is nothing but scoreboard item, the instance, right, is equal to item q dot pop rent. Okay. Next, reference model. Here reference model sequence SB item dot request comma prevent grant comma SB item, and passing all these arguments here. If SB item dot grant equal to expected grant. So what is SB item dot grant? Already whatever we have taken to the monitor, the grant data, that grant data is giving to the scoreboard, right? So we are checking actual grant data with the expected grant. If both are same, then what is the output statement? If both are not same, nothing but error, right? Not matched. So that conditions here. So here is the reference model. So here we have written reference model and passing the arguments, right? So here is the reference model to check the functionality. So task reference model, input logic, request, in-out logic, prevent grant, and communication request and grant. If prevent grant, what is the prevent grant? Prevent grant is nothing but before value. So if communication request is high, then grant equal to prevent grant. If communication request is low, then bus will be then we'll get the bus, right? So else if request 1 equal to 10, request 2 equal to 100, request 3 is equal to 1000, else grant equal to all zeros. And next state 10, whatever communication request. If communication request is high, then grant equal to previous grant. Previous value is same value is giving to the grant. Otherwise, the request 2 is high. If communication request is 0, the bus will be available. Okay. And remaining also. Check for these conditions here. 100, 1000, and all zeros, and default condition. Okay, everyone understood here? So if grant equal to 0000, and if previous grant equal to 1000, then previous grant equal to 0001. Else previous grant will be left to shift by 1. So what is that condition? Can anyone? What is that condition?
It's like if the fourth process has provided a grant previously, so next one should be the first processor. So that is the condition. Else condition means if it is not in fourth processor, maybe in 2 or 3, it goes to the next sequential processor.
Okay. So next one is the check phase. So what happens in the check phase? Check phase is nothing but comparison. Or if you want to do coverage analysis, you can do the coverage in the check phase. So next is base test. In the base test, here also created the environment. Sorry, first we'll go for environment. In environment, build phase and the connect phase created the agent. In the agent, there will be a sequencer, driver, and the monitor. And here agent, first we'll see agent. So in the agent, created active agent. Active agent means there will be driver, sequencer, monitor. Okay, so you know the difference between active agent and the passive agent, right? So same here. In the build phase, if get is active equal to UVM active, then both the driver and the sequencer instance is created and monitor also created. In the connect phase, connected. How we connected? For the driver, sequence item port to the sequencer, sequence item export. So what is the difference between port and the export? What is the difference between port and the export? So export will contain implementation details, right? Port will contain set of methods. So based on the target and based on the initiator, you can decide which one is the import or export, and the one is port. Okay, so that concept we already discussed. If you don't remember, just go through those concepts. So this is how we connect in the connect phase. Next, in the environment, top level, both agent and scoreboard instances just in the build phase created the instances, in the connect phase connected agent with the scoreboard. And top level test. What happens in test? We'll create the environment and the base sequence, constructor, build phase, run phase. So what is meant by rise objection and drop objection? What is meant by rise objection and drop objection?
Ma'am, we'll raise the objection to check the functionality that each component is working or not. And when the simulation is completed, and then all the objections raised are dropped.
Okay, so if you see in system error, we have how we have stopped the simulation by using the $finish or dollar stop, or by using event triggering. Events will be there, right? Events are there. And wait event. By using these, by using the comparison logic, we can stop the simulation. But whereas in UVM we have the object mechanism, right? We already discussed object mechanism, end of test objections. So by using objections, the simulator will automatically understand where at what time it can go to the extract phase. Okay, so then extract phase, then final phase, right? So for that purpose, mainly we use the rise and the drop objection. So all the components in the runtime, at what time it will start and at what time it will finish. Okay, both we need to check. So yeah, any other doubts? Everyone understood? So here we have taken task, run phase, phase dot rise objection, this, and base sequence created, and phase dot drop objection. So whatever the components, all components running in the run phase will start at a same time, but not finish at the same time, right? So that we can check by using the drop objection. Next is testbench.sp. So this is top level hierarchy. You know how it will be connected. Okay. No doubts, right? Up to here. So, done. So UVM warning, no warnings. UVM error, 6 errors. Next test done, 1. Base sequences 20. For driver 20, 48 for monitor, scoreboard 6, 19. So these all just counts, ID we have taken, right? For that counts, number of counts. Okay, see the output. So error, 6 errors is nothing but for not matched cases, it generated the error, right? Remaining all are matched cases. So base sequence inside body. So driver ID equal to 1, ID equal to 2, ID equal to 3, number of IDs. So request equal to all ones. So request equal to all one means what is the communication request? If communication request is 0, then only it will do the transaction, right? So here ID equal to 1, request equal to all 1, communication request equal to 0, but grant is 10, expected grant is 1. Both are not match. That's why error. Next one, here request equal to 10. This is the data. Okay, based on the data, what is the output? So ID 2, request equal to 0, communication request equal to 0, request equal to 0 means grant equal to 0. So expected grant also 0. Next, ID 3, what is the information given? ID 3, what the information got to the monitor and the scoreboard, scoreboard statement. So matched means ID equal to 3. That means the transaction request equal to 101, communication request 0, grant equal to 100, expected grant also 100. So both are match. And next, fourth one, here also grant and expected grant are match, but communication request equal to 1. That means what happened? No bus transaction will be happen. So previous data, whatever the previous data is there, again same data repeated. Okay, so grant equal to 100, expected grant is also 100, previous data only. And next, not matched cases, and again not match, and for ID 7, both communication request is 0, grant equal to 1, expected grant equal to 1. Next, 8th one, here also matched. Okay, here communication request equal to 1, so bus is not available. If bus is not available, previous data will be generated. Okay, so just compare all those so that you will get the clarity. Okay, everyone clear up to here?